Okay, great. So we are doing locally correctable codes. Let me remind you of the definition. Okay, so it's a code sitting inside sigma to the n such that there is a decoding algorithm. D, and it takes oracle access to some function R, a received word, and it takes in an input I, where, so such that if R from, so R is an element of sigma to the n, or has distance of R from the code at most delta prime, then for all I in 1, 2, 3 up to n, the decoder outputs the nearby code word with high probability. So the probability that over the internal randomness that D with oracle access to R on input I outputs xi is at least 0.99, where x in C is the unique, or is the code word. Well, x is the one that witnesses this, right? So has delta of x and R at most delta prime. This is the definition of a locally correctable code. It has oracle access to this string R, and it's going to make some queries into it. The local aspect of this locally correctable definition is that we want this decoder to run super fast, and it has to make few queries into R. Okay, so then the key parameters of this are so there's delta prime, the fraction of correctable errors. And then the query complexity, which is the number of queries that D makes into R, and the runtime, which we can hope is small. And we can hope for sublinear time, we can hope for a sublinear number of queries. And so these are the objects that we were looking to construct. And last class we saw a very nice example of that. These were the Reed-Muller codes, Reed-Muller locally correctable codes. So I'll write LCC. And if you remember, so they were given by FQ. You had a finite field FQ, then the alphabet sigma became FQ. And we also had an integer m, and the length n was q to the m, because we were evaluating polynomials on fq to the m. And there's a degree parameter d, which was 1 minus delta times q. And right, so the code was evaluations of polynomials of degree at most d over fq to the n. And that was what the code was, and it's and then we saw that its dimension k was equal to m plus d choose d, actually d plus m choose d, choose m, which is about 1 minus delta to the m over m factorial. And these were the locally correctable codes we saw last time. The local correction algorithm, when you wanted to recover the value of so you're given a received word R evaluated on fq to the m. You wanted to recover the value of the nearby polynomial p at the point alpha. So the idea was, let's pick a random line through alpha query all the points on that line. We get this is if the fraction of errors on that line is not too much, which will happen with good probability if we already have a promise that the overall fraction of errors is not too much. So the fraction of errors on the line is not too much. Then we have an instance of a Reed-Solomon decoding problem where the number of errors is not too much. So we can do the Reed-Solomon decoder and we can recover this value. And the query complexity, so the key point is that the query complexity, number of queries, is q, the number of points on a line, while the length of the code was q to the m. So this is now an mth root of n. And a very good setting of these parameters, one can make the number of queries down to polylog n, while still having everything while still having the rate being polynomial. So one can, so we can have n equals poly in k. This is the number of message bits. The overall length is polynomial, and q equals polylog of n, which is the same as polylog k. Q is sorry, this isn't q. This is queries and queries. And this setting of parameters is extremely useful, and it's very, very influential in PCPs and in hardness amplification and things like this. Okay, so this is already a very amazing code. The rate of this code, when I instantiated it this way with m growing, is not a constant. It is the output length is maybe the square of the input of the message length. The code word length is the square of the message length. In that case, the rate is little over 1. So one can also ask about LCCs in the high rate setting or positive rate setting, and in that case we're forced to restrict m to be constant, and when m is forced to be constant, so we get some positive rate which goes to 0 as m goes to infinity, but we can make the query complexity n to the epsilon for any positive epsilon, and this is what Reed-Muller locally corrected codes. So last time I also introduced multiplicity codes. And these are going to be much better in the high rate regime or positive rate regime, but way down in this setting they are no better than Reed-Muller. And okay, so multiplicity codes are a generalization of Reed-Muller codes. They have exactly the same setup: fq m and a degree parameter d, which we'll set later, and also a multiplicity parameter s. And we are going to be evaluating polynomials of degree at most d over fq to the m, but we're not just evaluating them, we're evaluating them to multiplicity s, which means we're taking the evaluation and the all derivatives of order less than s. So just to keep in mind, s equals 1 gives Reed-Muller. It is exactly Reed-Muller codes. Okay, so we'll have sigma equals, so sigma in this case is now bigger. It is fq to the m plus s minus 1 choose m. Okay. For it is the count of the number of derivatives you need. N is again q to the m, but it's now over a bigger alphabet. And the code C is order s evaluations of degree at most d polynomials over fq to the m. The dimension of this code, okay, so now I need to, so what's the dimension of this code? So what's the k? K is the number of information symbols. I have to be a little careful now about this. What's the k for this? What's the number of information symbols? If you remember the definition of k, it's not just the dimension of C as a vector space over fq. It is that number such that when you take sigma to the power that, it gives you the cardinality of the code. Right? And since we changed our alphabet from fq to something else, it became slightly more complicated. So k is equal to the dimension of C over fq divided by m plus s minus 1 choose m, because that's the number of fq symbols that yeah, so I mean I can even let this one step before. It is the dimension of sigma over fq. Since when we are working with a vector space whose when the alphabet is vector space over fq, then this is also a formula for fq linear codes, whatever that means in this setting. I mean, yeah. So this is this is just a quick way of calculating what is the case is that sigma to the k equals the size of this. The size of this, right, is just q to the power number of monomials of degree at most d. Because for every polynomial of degree at most d, we got a code. Q to the power that, which is d plus m choose m. Right? And how many q to the what power of q to the m plus s minus 1 choose m should you take to get this? It is this over this. So this is d plus m choose m over m plus s minus 1 choose m. And this is 1 minus delta to the m times d. I haven't told you what it is yet, but okay. So let me leave it as d to the m over m factorial. That's the numerator. The denominator, I'm going to choose s to be big, and then this becomes s to the m over m factorial. And now these m factorials cancel. There was an m factorial that was sitting here that made the rate necessarily go down, and now we're recovering that m factorial through some magic. But at the end of it, it's not totally done. So there is an approximately here, and so this is d over s whole to the m. And this is what the dimension of the code turns out. So the big question now is how large can I take the distance d, the degree d, while still having positive distance? The fact that we're evaluating higher order derivatives means that there's more distance between polynomials. So maybe it allows us to take very high degree while still preserving distance. Okay, and so this is the multiplicity. So there is a lemma now which answers this. This is the multiplicity Schwarzschild lemma. And it says that polynomials of degree d, it's very similar to the other case, but so let me say this. Okay, so I need to talk about this higher order evaluations and higher order evaluations, and then I can talk about order of vanishing. Okay, so just like the exercise on the worksheet, we talk about the multiplicity of vanishing of p at the point alpha. So this is the definition. We have p of x1 up to xm, and we have a point alpha in fq to the m. Then the multiplicity of vanishing of the point p of the polynomial p at the point alpha is equal to the largest s, such that all derivatives of p up to order s minus 1 vanish. dp by di over dx1 to the I1, dx2 to the I2, dxm to the Im of p. So that p part is done. Yeah. So that's some polynomial at the point alpha equals 0 for all I1 up to Im. This is I1 plus Im, because that's how derivatives work, such that I1 plus etc. plus Im is at most s minus 1. So there's a lot of words. When s is 1, we are asking that the 0th order derivative, namely just p itself, vanishes at alpha. When s is 7, we are okay. Let's one step back. When s is 2, we're asking that dp by dx1 is 0. First of all, we're asking that p is 0, and also that dp by dx1 is 0, and dp by dx2 is 0. All the first order partial derivatives are 0. This is the same as the gradient of p is 0. Okay, so that's the definition of higher order multiplicity. For univariate polynomials, it is the same as x minus alpha whole to the power s divides your polynomial. Okay.
So this is for a given alpha.
This is for a given alpha. Yes. The vanishing vanishing multiplicity of p at the point alpha is this largest integer. Where are these derivatives? Derivatives, the definition of derivatives are slightly delicate. So if you're in positive characteristics, sometimes derivatives don't work well. So you should use some variant of derivative called Hasse derivative. It is whatever that makes the Taylor series formula or the Taylor expansion formula for polynomials work. It's there on your worksheet, the definition of this Hasse derivative. It's very closely related to this derivative. It's off by a scalar. That scalar is sometimes 0 or infinity in characteristic p. So that one turns out to be the right definition. It is not the definition where you take the derivative of x to the j. It's not repeated applications of the first derivative. It is something else. It directly defines the 10th derivative of a polynomial. By removing some constants that automatically show up. Okay, this is the definition of multiplicity. It is closely related to these order s evaluations, because if two polynomials have the same order s evaluation at a point alpha, then their difference vanishes with multiplicity s. And that it captures exactly. Good. So now I can say the multiplicity Schwarz-Zippel lemma. It is a generalization of the usual Schwarz-Zippel lemma. It says that the expected over a random point alpha in fq to the m of the multiplicity of vanishing of p at the point alpha is at most d over q, where p is a non-zero polynomial of degree at most d. That's the multiplicity Schwarz-Zippel. How does it relate to the usual Schwarz-Zippel lemma? It implies it, right? The multiplicity, if p vanishes at alpha, the multiplicity is at least 1. So this is counting zeros, but it's counting them with multiplicity. So if you happen to know that your polynomial is going to vanish with more multiplicity, you can get the number of zeros, you can get that reduced. The number of such points where it vanishes with high multiplicity is reduced. Right, so the number of points where, the probability that p vanishes at alpha with multiplicity 2 is at most d over 2q, just by this and Markov. Okay, and the proof of the multiplicity Schwarz-Zippel lemma, if you know the statement and you go into a room and you need to prove it to come out, you will come out. The proof of Schwarz-Zippel itself has one trick in it. Right? It's not totally obvious. There's a trick, which is, if you have the polynomial f of xy, write it as summation fi of x times y to the I, and then consider the largest I where fi of x is non-zero. That one line is the trick of Schwarz-Zippel. That's why the Schwarz-Zippel lemma is. It took time to prove it. Okay, so being aware of that trick and going to the room, one will be able to prove this. Okay. You have to make some claims about multiplicities of various of these fi's. You do the same trick of writing it as summation fi of x y to the I, and then you have to consider the fi's and you have to make claims about multiplicity related claims about the fi. Okay, so this is the claim, but this is the statement that's going to give us our distance. Yes.
Sorry. There is an alternative proof for the original Schwarz-Zippel lemma by Dana, right? Like this projection on the line. Does this technique work for this one as well?
Yes. So this alternate proof is by who? Can you remember? Dana Moskowitz?
Yes.
Dana Moskowitz. Yes. Okay. So I know that proof. Yes. So that proof, that style of proof will also work here. There's a key part of that proof, which is Yeah, so that proof is based on pick a random line, look at the restriction on that. That proof requires that every polynomial is non-zero at least once. Every non-zero polynomial has at least one point of being non-zero. That fact is somewhat easy to prove in the multiplicity 1 case. When you have this multiplicity case, it's not that easy to prove, but it is true. So in order to make that proof work with the projection onto line, you need to prove that a polynomial of degree at most d has at least one point where it does not vanish with full multiplicity. And that already requires a bit of work. But yes, a similar strategy will work in this case. There is a version of this statement where fq to the m is replaced with a set of size q, or maybe fq is replaced with set a, and then you do d over size a. That kind of statement cannot be proved with the restrictions to lines, but yeah.
Okay. Thank you.
Okay, great. So we are now ready to use the multiplicity Schwarzschild lemma to give us a bound on the distance of this code. Good. So take P1 and P2 of degree at most d and distinct. Consider the code words corresponding to P1 and P2. Then the fraction of coordinates where the code words agree this is exactly the fraction of alpha is the probability over alpha in fq to the m that the order up to s evaluation of P1 at alpha equals the order up to s evaluation of P2 at alpha. This is, if you remember, the tuple of all derivatives of order up to s. This is the same as, by linearity of derivatives, that P1 minus P2, that polynomial order s alpha equals all zeros, right? This is the vector of all zeros in sigma, and this is exactly the same as the probability that P1 minus P2 vanishes with multiplicity s. Multiplicity of P1 minus P2 at alpha is at least s. Okay, and by the multiplicity Schwarzschild lemma and Markov, this is at most d over s cube. So we are getting this. So this is the fraction of agreements, right? So we are happy if this is less than, let's say, so we want this to be at most 1 minus delta, if you want eventual distance delta. So this is telling us that we should set d to be not 1 minus delta times q, but s times 1 minus delta times q. Okay, so this is how we set it. D equals s times 1 minus delta times q. It says that polynomials of degree all the way up to sq are not totally zero when you evaluate multiplicity. Yeah. So you get non-trivial statements all the way up to degree s times q. So we are evaluating polynomials of much higher degree than the size of the box that we are evaluating. Or we are allowed to do that if we take s big. Okay, good. So then this gives us, so now once d is s times 1 minus delta times q, I can finish this line. This is s times 1 minus delta q over s whole to the m. And this is 1 minus delta to the m times q to the m times n. And so we got from this the rate is 1 minus delta to the m. And this gives us codes which have rate close to 1. It is not the optimal trade-off between rate and distance. The optimal trade-off would have been rate equals 1 minus delta. Now we are paying, as you increase the number of variables, we are paying for it by increasing the, by reducing the rate, worsening the rate distance trade-off. Yeah, but it is, I mean, it's able to at least achieve rate almost 1. Okay, so I mean, so for this to finally give us something, we need to do local correction of these codes. But since they were defined based on things like polynomials and derivatives, which are nice, yeah.
So the gain of our derivative regular codes is simply m factorial.
Yeah, the gain is exactly just that m factorial.
But now we'll still need m to be constant.
We will still need m to be constant to get
Constant
positive rate. Correct. The moment, if you want delta positive and m super constant, that's it. The rate is no longer positive. So you can only see this gain if m stays small. Question, Ted?
And we're also going to end up with a larger alphabet size?
Yes, we are ending up with a larger alphabet size, much bigger, but it's a big constant. But then when you want to compare this with that on an even playing field, you concatenate down to binary, and you will preserve the goodness of this, and the alphabet size you hardly pay for. Okay. So let's see local correction. So I will do it in a simple case for higher order derivatives and more variables. It's just yeah. There's nothing fancy going on. It's just being careful. Okay, so here I have this received word R. It's actually equal to P plus some noise, and this was the noise. Okay, so there are some points where things got corrupted, and I want. So what is the problem? So this is the local correction problem, right? I'm solving local correction. So we're given some alpha in fq to the m, and we want p evaluated to up to order s at the point alpha. Okay, so I'm now going to fix m equals 2, so it's 2 variables, it looks like that. And I'm also going to fix s equals 2 for now. Okay, so what do I want? In this case, I want p of alpha dp by dx of alpha dp by dy of alpha. And yeah, so and there is this polynomial p of xy, and r is close to it. Okay, so what can I do? Here was alpha. As before, and we don't have much available to us. As before, we can pick a random line passing through alpha. So let's pick a random line passing through alpha. What do we get from this? So pick random beta, and we look at p of alpha plus beta t. Okay, define h of t, which is p of alpha plus beta t. Let's pretend also for the moment that the degree d, so I set m equal to s equal to 2, and we'll pretend the degree is something like 1.9 cube. I'm allowed to do one. This is where the action is, when the degree has gone above the field size. If degree is just less than q itself, then we can already do, standard Riemann decoding. Okay, so degree has gone above 1.9, has gone high. Okay, so as before, inspired by what we did in the Reed-Muller case, we pick a random line and we can look at that line. What do we get out of that line? We would like to get h of t. This is our hope. And what we see on that line, is that a Reed-Solomon code word? Well, sort of. It is, we have at this particular point, we have the evaluation of p, we have the directional derivative of p in x direction, the directional derivative of p in the y direction. From that, we can get the directional derivative of p in the line's direction. This is by the gradient. That is dh by dt. Right? If this is h of t, then by the chain rule, right? So of course, h of any for any little t, h of little t is p of alpha plus beta t. That's fine. But what is h prime of t? So what we are going to recover on that line is not a Reed-Solomon code word, but it will be a univariate multiplicity code word. And we know that univariate multiplicity codes have distance, of degree. They're again of the same degree, so they also have distance delta. And so, hopefully we'll be able to recover them using a Berlekamp-Welch type algorithm. So, okay, so we will try to recover both h and h prime. This will make us get a univariate multiplicity code word. What is h prime t? It's not, so it has to, you have to do something with this, right? It is, I guess, beta 1 times p of dp by dx, right? I'm using the chain rule, right? You know how you take derivative of a thing with many variables in there? You take d by dx of this, and then take the derivative of d by, so I'll just write it, dp by dx times beta 1 plus beta 2 times dp by dy at the point alpha plus beta t. And these are things that are available to us, dp by dy and dp by dx. So these were the two directional derivatives in these two directions. Combining them, we got the directional derivative in the direction of the line. So we got h and h prime t. So we have h of t, h prime t for all t in fq with some possibly wrong, This is exactly an instance of univariate multiplicity code decoding, and there is a nice generalization of the Berlekamp-Welch decoding algorithm which we saw in the first lecture to the problem of univariate multiplicity code decoding. Question?
So in some sense what we're getting here is because like both of these derivatives are bundled up into one alphabet symbol, like if you're going to corrupt one, you have to corrupt both of them.
Right. If I got this one right and that one wrong, it won't help me get any of the directional derivatives. So we may as well bundle it up as one. So it's good to bundle it up just because of this reason. It also helps us get the errors in a bundled fashion, right? So we don't lose in the budget.
Just saying what you said again. If you because we are encoding all the derivatives in the alphabet itself, you either when you get something right, you get all of them right. You retain all the information.
Correct. Right. So one could have taken the same code and unbundled it, and you would get a code over fq, but it would be of length q to the m times m plus s minus 1 choose m. But then the trade-off between the number of errors and the correctable errors would not be so great. The bundling, because we have a way of using simultaneous correctness of things, it helps us a lot. Okay. And so the algorithm is, okay, then do the univariate decoding, and we get, so from this, do univariate multiplicity decoding, code, decoding, get h of t, the formal polynomial h of t. Compute h of 0, and this is just p of alpha, and we got the value of p at alpha. Are we done? Right, we're not done. The definition of locally correctable, you went to a bigger alphabet, you have to pay for that too. You have to not only recover p at alpha, you have to recover dp by dx at alpha and dp by dy at alpha. The problem of local correction is finding the symbol at the point alpha. So we want this whole thing, right? So we need dp by dx at alpha and dp by dy at alpha. So what do we do?
So from h prime 0, we get a linear combination of del B length and del B denominator. Take another beta, you get 2 linear combinations. And
Right, very good. So h itself didn't just give you h of 0. You also have h prime 0, which is dp by it is this linear. It's a certain linear combination. It's the derivative of p in direction of the line. Okay, so you got the value of p here. You also get the directional derivative in this direction. When you did the decoding, it gives it to you for free. We got the value and the directional derivative in this direction. It's quite good. We eventually wanted dp by dx and dp by dy, but dp by dx and dp by dy together are just a proxy for all directional derivatives in all directions. And if you get any two directional derivatives in linearly independent directions, that's enough to recover this entire directional derivative, or the gradient vector. So the algorithm is now take a totally different direction at random again. Again, we hope that there are few errors on this line, and then get the directional derivative in that direction. And again, we hope now that these two directions are linearly independent. In this case, it will always be linearly independent. They're not equal. And then we do it again. So repeat with another beta prime, and use the directional derivatives in directions beta and beta prime to get dp by dx at alpha and dp by dy at alpha. And that just worked. If you increase the multiplicity parameter from s to from 2 to 3, then you would want first derivatives and second derivatives. Then you would need more lines, right? And you don't need them linearly independent. You want them. I guess linearly independent in this case is enough, right? And then as you go to more variables, something else happens. But whatever happens, it's all very predictable. Right. So the final algorithm is at the point alpha, send out many random lines in many directions. How many different lines? At the end, you will need as many lines as the number of pieces of information you need. So here we sent 2. Oh, I see. I guess here we will need just the total number of highest order derivatives. So it's slightly less than that. Good. So we send lines in many directions. We recover on each one of them. We do a univariate multiplicity code decoding, and we get for the point alpha the value, directional derivatives in various directions, second order derivatives in various directions, etc. And we get all this information, and some linear transformation of that will give you this. Yes?
So in order to get, the kth order derivative right, I need to sort of get k lines where I successfully decode the kth order derivative on that line.
Yes, you do need k lines. The way I said it, you need k lines to.
Can I do some sort of amplification before that step, so I don't need to pay, factor of k in my probability of decoding a line correctly?
Yes, that's a very good question. So the issue is if the more lines you send, the more you need many different lines to have a small fraction of error. So you have to union bound over the probability that each line is good. So yes, there is some built-in robustness to the decoding problem at this point. So if you send it out at even more lines, the problem that you get is the problem of recovering a polynomial from values. And polynomials are error correcting codes. So if you give me values of polynomials with some redundancy, then it's okay even if some of them are wrong. So there is some built-in redundancy, so you can get away with, so instead of taking the exact minimum number of lines, if you take in twice that number of lines, then it's okay if 1/10 of those lines are wrong. But then it becomes a polynomial decoding problem at this point, and then you just solve that and you get and that makes it robust. And from that you can make it decode from delta over 2 fraction errors or delta over 4 fraction errors. Okay, good. Questions about this local correction algorithm? So the final query complexity. So these were the parameters. Let me write it here. Query complexity of local correction from delta over, let's say, 10 fraction errors. To get the delta over 10, you need to do this extra idea that I mentioned, where you don't want delta over the number of lines. You want delta over 10. You need to have this built-in robustness in how you take more lines than you need, and you do some error correction at the end. So the query complexity of this equals if this m plus s choose m. I will just call it s to the m. So order of s to the m times q, which is the number of points on a line. And this compared to the length of the code is, so this is basically n order of n to the 1 over m when s and m are constants. Okay, and to make, so somewhere in here I did this approximation, right, that m plus s minus 1 choose m is like s to the m over m factorial. This was so that I could get the m factorial, which cancels this out. This approximation is only okay if s is much bigger than m already. So we need and s is much bigger than and so we need also s much bigger than m to the, let's say, 3 for rate to equal 1 minus delta to the m. So at the end of all this, we got rate and rate and distance having some trade-off, which is at least lets them be constants. Let's say constants with the rate being close to 1, and the query complexity is n to the epsilon, where n is the length of the code. Okay, questions? Yeah.
So where did we gain from regular codes? What did we do?
The only thing we gained is we are able to reach rate 0.8 with so rate 0.8 is not achievable with the sublinear query complexity with read-mother, and for read-mother there's this trade-off that if you want a query complexity n to the epsilon, the rate has to be less than 1 over epsilon factorial or something. And now if you want a query complexity n to the epsilon, the rate can still be any positive rate you want. It can be 0.9. But it comes at the cost of the distance being, no, it's not without loss. The distance, sorry, I don't know if it's not without loss. It has positive distance and this, but the distance will be some constant depending on the target epsilon for query complexity n to the epsilon. Yeah. Okay. So my plan now is to describe the Alon-Edmonds-Luby transformation on codes. It's based on expander graphs, and it's going to take all this and give you a locally correctable code with rate distance trade-off optimal. Rate equals 1 minus delta. So we struggled very hard to get some positive rate, but then now we will take this and through some other magical transformation, we will then boost it to optimal rate distance trade-off. Without using much. So what's needed ends up being very, very little. But okay, so this is what I plan to do now. So questions about what we saw just now, or what we're going to do?
Very high level, so what parts are going to change now? So where did we fall short?
Where did we fall short? The only place where we fell short is rate is 1 minus delta to the m, where m is a constant depending on the target query complexity that we want.
And this came in because we didn't know how to do better than multiplicity Schwarzschild lemma, or
You mean what's missing in this?
yeah.
I don't know. And maybe there are more functions you can add into this code for which the local decoding is possible. I don't know what exactly to blame. Yeah. I mean, the multiplicity Schwarzschild lemma is tight for this set of polynomials. But maybe there are more polynomials which one could squeeze into this. But while also getting local decoding, I don't even know that we should expect it. Yeah. Okay. Okay, so now we will see a way of improving the rate distance trade-off. So before that, I want to so this will help us later, and it's also a really good example. We will So I want to consider the case of random errors. Random errors. How do we get a code that is good against random errors? So let me give you a code with okay, so in fact I'll give you a really amazing code. I'll give you a code C in 0, 1 to the n with lying on the GV bound. That can correct random errors. So let's say a G bound with R and delta, right? So R equals 1 minus h of delta or something that can correct delta over 2 minus epsilon fraction random errors. So you see the problem. So you see what I'm doing. I'm giving you a code which is amazing. It achieves everything that we wanted to achieve, except it's only doing it against random errors and not adversarial errors. Okay, actually, sorry, I lied to it. So that's not the rate and distance of the code. Yeah. So of rate R such that for delta satisfying R equals 1 minus h of delta, we can correct delta over 2 fraction random errors. I'm not claiming that the distance of the code is this. It's just that I claim that I can correct delta over 2 epsilon fraction random errors. If these were adversarial errors, since this code itself does not have distance delta, the adversarial errors can mess up this code. Okay, this code is going to be extremely simple. It is a code we've already seen. It is Reed-Solomon codes concatenated with a brute force search code inside. Okay, so we'll take a Reed-Solomon code of rate 1 minus epsilon and distance and distance epsilon, because that's what Reed-Solomon codes achieve, and we'll concatenate with a brute force search code of length log n, because that's what you concatenate Reed-Solomon codes with, right? Because the alphabet size is n, so it's over f2 that can be recovered from delta over 2 fraction Yeah, so this brute force search code is going to have rate r, and it can be recovered from delta over 2 fraction errors. So this lies on the GV bound, and distance delta with r equals 1 minus h of delta. And in particular, it can be recovered from delta over 2 fraction errors. And we're concatenating these. So just let me draw the picture. So here we took a Reed-Solomon code word, and it had a whole bunch of symbols, big symbols. Then each of these big symbols got expanded using our brute force search code, which is binary now. Is okay? So this is in fq to the n, where maybe q is order n or something. Right? That's how Reed-Solomon codes work. But this is rate nearly 1. And down below, we have a code with the rate r and distance 1 minus h of delta. Distance delta, where r equals 1 minus h of delta. So we have concatenated a code with rate nearly 1 with a code of rate r. What is the resulting rate? The product, which is r times nearly 1, which is nearly r. What is the resulting distance? The product. So this is nearly 0 times delta, which is nearly 0. So this is terrible. But it's robust to random errors. So let's do it. Why is that? Suppose random errors happen. Okay, so we're putting delta over 2 minus epsilon fraction random errors. How many errors are going to happen in this block?
That fraction.
Around that fraction. How many in this block? Around that fraction. In all the blocks, it will be around that fraction. Well, not all, almost all, because it's random. So in most blocks, it will be the around the fraction delta over 2 fraction. So those can be corrected by the inner code. Then when they go up to the Reed-Solomon, they're perfect. There's no trace of any error. Only a tiny fraction, epsilon fraction of these blocks have seen an error. Those go up and the Reed-Solomon code corrects them. Okay, so this is yeah. So I didn't write anything, but okay. So this, yeah, I didn't write anything. This was a movie. Yeah. So let me say it again. Suppose delta over 2 minus epsilon fraction random errors occur. Then most of these blocks will see only delta over 2 minus epsilon fraction random errors, and nothing will see, or very few will see delta over 2 fraction random errors. Those blocks that see delta over 2 or more fraction errors, the inner code cannot correct. So when we do the inner code decoding, the symbol that we send up to the Reed-Solomon code will be wrong. But most of them we get it correct. So they go up to the Reed-Solomon code word and they are all correct. Yes?
Isn't there like some off by constant or something like that? Because if we get epsilon errors in the code below, Reed-Solomon can only correct epsilon over 2, right? You can't correct epsilon.
Yes. So my I'm slightly fudging with the different epsilons. So yeah. So all my epsilons have to be adjusted to finally get this, but they're all within epsilon. So if I say order epsilon here, I think maybe you'll be okay, and then everything I said is correct. Yeah. Okay. So random errors are much easier to correct than worst case errors, because we somehow know. Then concatenation just solves the problem. Yeah.
So does this code achieve Shannon capacity?
Yeah, so then this will achieve Shannon capacity, except you have to not put in a GV code meeting the GV bound. You take a code which can meet Shannon capacity, which is something different. So if you concatenate, you will get a code that meets Shannon capacity. So it will achieve the r equals 1 minus h of p, where p is the fraction of errors. It will achieve that up to a minus epsilon. The catch is the running time of everything will be exponential in 1 over epsilon, where epsilon is the gap to capacity. And it was a famous open question. Well, the coding theorists didn't even know how to say it, but it should have been a famous open question for 50 years, but it was only a famous open question for 20 years. That can you do it with polynomial in 1 over epsilon thing, and this was very recently solved by polar codes. So those codes are, they achieve capacity, but they are terrible from the point of view of worst case errors. Okay, so this was random errors. This is going to help us in how we get codes with the optimal r versus r equals 1 minus delta, locally correctable codes. Okay. So this is a self-contained nugget, but it will also help us in what I said. So this discovery was also by Forney back then, when he discovered concatenation in the 70s. Okay. So LCCs with R equals 1 minus delta minus epsilon. So let me start with the construction that is a locally correctable code that corrects against random errors, delta over 2 fraction random errors. Then we'll make it worst case. That's actually the miracle. So, okay, so start with a code word of our LCC. So we're going to actually we first fix an outer LCC with rate 1 minus epsilon and distance epsilon. We're going to do something similar to this, except we will, instead of using a Reed-Solomon code of rate 1 minus epsilon, we will use an LCC of rate 1 minus epsilon. Okay, so this is, so we fix that outer, but it's an LCC. So we fix that out, and we start with the code word, and now we're going to concatenate. So I just transpose the picture, but it's the same. And each one of these I concatenate to get okay, I'm going to concatenate it this way. Okay, so I concatenate and I get, we concatenate with an inner code which has rate equals 1 minus delta. Okay, so for example, Reed-Solomon. Let me even fix it to be Reed-Solomon, an inner Reed-Solomon code. Okay, so this code had rate 1 minus epsilon. This code has rate r. So the total rate is 1 minus epsilon times r, which is basically r. I want to say that this resulting code is an LCC from random errors, and it's the exact same argument. Suppose you, how does that work? Suppose I want a particular symbol. I cannot guarantee, I cannot count on less than, so let's assume that delta over 2 random errors have occurred. I cannot hope that the symbol that I'm looking to decode had less than delta over 2 errors inside that block. And there will be some blocks which have more than delta over 2 errors, and the whole point of an LCC is to get it for all I. Okay, so let's, I don't want to take probability over the errors also when I'm doing this. Okay, so good. So I want to get this particular one. So in order to get this particular symbol, it suffices to get this particular Reed-Solomon code word. In order to get this particular Reed-Solomon code word, it suffices to get this particular symbol, because that Reed-Solomon code word is just, it's just take that symbol and encode it in the Reed-Solomon code. So I want to get this symbol of this LCC. So I can run the local correcting algorithm for this LCC. What it would have done is it would have queried a few of these locations. These locations are random and all over the place. Yeah. Every time you want a particular symbol from the outer LCC, you go into that inner Reed-Solomon code word. What is written on the received word over here may or may not be correct, but if it's within delta over 2 of a Reed-Solomon code word, you can correct it and take that. And correct it, send it back, and feed it to the LCC decoder. And this overall algorithm does decode from random error. So this was just some high level view of how to get an LCC that corrects against random error. All you needed is to implement the same scheme, but with your outer code being an LCC of rate 1 minus epsilon. Okay, so now we're going to do this is the Alon-Edmonds-Luby expander transformation. So okay, so I have here we have n little code words written down. I'm going to take a big expander graph on these vertices. Okay, there are n, and I'm going to take an expander graph which has n vertices on the right, and I'm going to do something with the symbols that have been written. So the high level idea is, so what I'm now going to do is give you an LCC that is robust to adversarial delta over 2 fraction errors. And how are we going to do it? We're going to take adversarial errors and pseudo-randomly permute them to make it look like random errors. And then that scheme will fix random errors. Okay, so I write here, so let's say this is degree, I can't use D, so it is, oh, can I use D? Maybe I can use D. I use D inside multiplicity codes, but we're not going in there again, so D is free, I use D. Good, so we took a Reed-Solomon code, this inner Reed-Solomon code, I'm going to call its length D. Okay, so we have n Reed-Solomon code words, each of length D, and this is a Reed-Solomon code of length, so I'm writing that down, length D, rate R, distance delta equals 1 minus R. Okay, these are the best R versus delta trade-off codes, and there are length D and there are n of them sitting down there. And we have taken a bipartite expander graph which is D-regular on both sides, and there are n vertices on the right also. And we're going to do the following transformation. All these D symbols that were written, we will write them on the edges here and send those symbols down those wires at every vertex on the right. So if 6 was written here, it got sent here, 6 got received here. I gather all the symbols that are coming in and I write them down here. And so this is a Reed-Solomon code of blah 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 of alphabet size, let's say sigma 0. Then this alphabet is going to be sigma 0 to the D. We gathered all the D symbols and we wrote them as a tuple, and that is going to be the symbol of our new code. So what this was a transformation that took an n by D matrix of symbols from sigma 0 and gave you a vector of length n with symbols from sigma 0 to the D. And there was some pseudo randomness coming from the expanders sitting in there. And it has some property. The property that it has is, so the act of bundling symbols and making a bigger alphabet, this is a very powerful thing. We already saw it in multiplicity codes how it worked. What it's doing is it's making you worry only about certain error patterns. Right? Instead of having all these symbols naked, dn of these symbols lying around, we have them bundled in a very careful way, so that if some adversarial error pattern happens here, the kind of errors that are felt on this side are are limited. Okay. So the heart of the reason this expander is going to help us is, suppose some alpha n errors occur, and these are adversarial errors. Okay, so we have a set of alpha n coordinates on the right, where what was written has been completely corrupted, and we cannot trust that anymore. This is how we can correct these errors. Send the symbols back. So wait, do you know what I'm doing? I have what I described is a transformation from this n by d matrix where each row is a Reed-Solomon code word into a long vector of length n over the alphabet sigma 0 to the d. I'm showing you how to correct adversarial errors in this setting. Yeah.
The question is, you have n code words, right?
Yes.
So what's the new, because the new code word, what you get on the right side?
The new code word is going to be so the new code word is in sigma to the n, where sigma is sigma 0 to the d. And so we are treating sigma as the alphabet and n as the length. So when an error occurs, it affects that whole thing. Okay, so I'm showing you how to correct alpha n adversarial errors. Suppose alpha n of these right-hand side blocks have been changed to something. How are those errors felt on this side? Well, so I proposed, there's a very natural decoding algorithm to do. At each block here, I'm not doing this locally yet, I'm just describing how to correct it. For each Reed-Solomon code word here, get the symbols back from what has been written on the right. Right? So 7 was written here, it comes back as a 7, and I get the 7 back here, and 7 actually came from somewhere here. So there was somewhere here, there was a 6, and that 6 got sent. So get the symbols back from the right-hand side. This would give you a candidate Reed-Solomon code word, but it may not be right. Some of these may be wrong. How many will be wrong? The number of neighbors that are inside that alpha and adversarial errors. How many should there be? About alpha fraction. The pseudo-randomness of the expander guarantees this, that for most vertices on the left, the number of neighbors inside that set of size alpha n is about alpha. The fraction of neighbors, so the number is about alpha d. Good. But there are some where it's not. But for most it is right. So if alpha is less than delta over 2, and this is a Reed-Solomon code which is robust to delta over 2 fraction errors, each of these Reed-Solomon code words, most of them will be correctable. So we do not even have to see these errors. And so there will be just a tiny fraction of Reed-Solomon code words which do not get corrected correctly. And this will be a small fraction of errors which our outer LCC will be able to correct. Okay, so this is the overall strategy. So I didn't say why this is L, but why this is a locally correctable thing. But I just described a decoding algorithm, and now we just have to make sure that everything can be done locally. Yeah.
Does this say more generally that if you can correct random errors,
Uh-huh.
you can actually always...
Okay, that's a good question. Yeah, so what did we pay? We paid for this in some way. How did we pay?
Alphabet size is
The alphabet size went up. So, so when you are talking about the problem of getting binary codes meeting the GB bound, we can't do that
We can't.
because the alphabet, because the alphabet went up. Yeah.
What did we pay? I'm asking, what did we get from this? Because we need to find the outer code, right?
Yeah.
The outer code is the bigger one.
Yes. The bigger code is of length n, so it's not a brute force searchable thing. Yes.
Yeah, so then we just make it worse.
Good. What did we gain? So we reduced the problem of finding an LCC to a problem of finding an LCC.
And actually that corrects adversarial errors when
No. So at this LCC, You remember this LCC, the one that comes before this that made all these read-solvent code words? That had to be worst case errors too.
Oh.
The LCC that's sitting here, we have to basically do worst case, or we don't know. I don't know. Maybe we could do. Yeah. Okay. So nobody is guaranteeing that those read-solvent code words that are truly corrected, that cannot be corrected, are distributed randomly. So I'm not guaranteeing that. It's just that their number is small. What did we gain? We only need a LCC with high rate, and its rate distance trade-off did not matter. Now multiplicity codes have a bad rate distance trade-off, but it doesn't hurt us. So this is what we gain. So we will take a multiplicity code with rate 0.99 and distance terrible, and transform it into a locally correctable code with rate NER and distance delta being 1 minus R. So it will be the optimal trade-off. So while multiplicity codes when you tune their parameters, you don't get the good rate distance trade-off. Just the mere fact that you get positive fraction distance with high rate is enough to.
But you assume you start with the optimal rate distance, right?
No, that was only for the inner code. The outer was 1 minus epsilon, and distance, okay, anything, some epsilon prime. Yeah, and but here the inner read-solvent, we used it for all values of R and delta. Yeah.
How sensitive is this to the quality of the expander? Like, how good do we need our expansion degree trade-off to be?
Yeah. So we need. So I know that if the eigenvalue is poly d, so there's a d to the 0.9, for example, it will do everything that we can hope from this set.
So,
Yeah.
here you need the mixing lemma?
Yeah, the expander mixing lemma is which gives the sampling property of expanders. So that whenever you have a set of alpha n on the right, the number of neighbors there the number of vertices there which have more than alpha plus epsilon d fraction neighbors in the set is less than some very small.
So what's the final distance for this code?
The final distance for this code is, we correct delta over 2 fraction adversarial errors, so its distance is delta. And the rate is also, everything is up to this up to some epsilon, but yeah, the rate and our distance have R equals 1 minus delta. So we will see. So let me just see that it's an LCC2. I don't need to merge these two pictures, right? You see what happened, right? This we took an LCC. This is going to be a multiplicity code with rate 1 minus epsilon. We get read-solvent code words, and then I just moved over to this picture and redistributed the symbols in some way, treated different bundles of letters and called that an alphabet, and this gave us a code. So yeah, so final code has rate some R minus epsilon and a distance delta minus epsilon, and it's also an LCC. Yeah, this step is basically a distance amplification step. It starts off with a code with really small distance, that outer LCC, and it brought it up to delta, and we get an LCC with what's the query complexity? I need to say what the query complexity is. So how do we run the decoding, the LCC decoding algorithm? Let's say you want this particular symbol of your code word. In order to get this symbol, so go back along these edges, and it suffices to recover this read-solvent code word, and maybe this read-solvent code word, and maybe this read-solvent code word. If you recover these 3 read-solvent code words, they have within them enough symbols to tell you this. So we need to recover these 3 read-solvent code words. So we will now run, we'll go back to our multiplicity code. So I guess this and this. We will, getting this read solvent code word is the same as getting this symbol from our outer LCC. So run the LCC decoder, the local decoder for that. It will make queries into various coordinates. Those coordinates that it queries, you go back here, get the corresponding read solvent code word. How do you recover it? You recover it by querying things from the right. But this is that's a constant degree D expander. So I mean everything is blowing up by factors of D here and there. But you're basically running the LCC here with a poly D factor blow up. So you get an LCC with final query complexity. Poly D times old query complexity, or times query complexity of the big LCC. And the D that you need to take for all the sampling things to happen, we need so we need to take D to be poly of 1 over delta, and this just works. Okay, so let me say one last thing about this. Yeah, so the way everything here works, it actually allows you to so this even happened here. I swept it under the rug. How many of these inner codes are not decoded correctly? I said some epsilon fraction of them are not decoded correctly, but actually it's little over 1. There's a Chernoff bound here, right? If so remember the setup where it is random error setting. Delta over 2 minus epsilon fraction of all the bits are corrupted. So what fraction occurs here? What's the probability that if delta over 2 minus epsilon fraction of the bits are corrupted, more than delta over 2 errors occur here? It's exponentially small in the length of this block. The length of this block is log n. So it is exponentially small in log n. It is some 1 over poly n. So the probability that a certain block is not decoded correctly is 1 over poly n. So maybe let's say some square root n of these blocks are not decoded correctly. So actually you didn't need your read solvent code to have constant distance even. You just needed it to have distance square root n. You didn't need it to be epsilon n. You needed it just to be square root n. So you could start actually with the read solvent code with distance square root n. Here also you could start with an LCC which is robust to a really small fraction of errors. Realizing that, you can go back into your multiplicity code and take m to be super constant, and it will end up giving. The multiplicity codes with m being super constant were never discussed because the problem of give me an LCC with sub-constant error resilience was never called a problem. But it's a thing, you can define it. And it is exactly what will fit into this whole thing. So if you then do that, at the end you can get LCCs robust to LCCs with even smaller query complexity. The fact that you can increase the number of variables m to even more, and m was determining the query complexity of your final of the multiplicity code decoder, that whole thing pieces together and gives you an even better LCC. So taking so I'll just wrap up this section by summarizing the final result. So taking m equals omega 1 in multiplicity codes, and I can say what you take the degree to be. So the degree will then be s times 1 minus 1 over m, maybe a little over 1 over m, times q. We get LCCs of rate 1 minus epsilon, robust to how many fraction errors? Yeah, some subconstant. Yeah, let me fix something. So we say 1 minus 1 over m square to theta of 1 over m square fraction errors. And with query complexity n to the 1 over m. And so in the final setting we would set m to be about square root log n, and good things will happen. So it's robust to a sub-constant fraction of errors, and it has even better query complexity than n to the epsilon, because m went to little omega 1. And combined with the AEL transformation, AEL, this gives LCCs with r equals 1 minus delta minus epsilon, and 2 to the square root log n about query complexity. Okay, and this is the result of with Or Meir, Nogaron Zevi, Shubhangi Saraf. Okay, good. Questions about this? So it was an unexpected surprise after doing the AEL transformation that it is also going to reduce the query complexity of the LCC, because it suddenly opened up the usage of LCCs which have sub-constant distance. So that is the ultimate object that one needs to construct. High rate LCCs with sub-constant, even with sub-constant fraction errors. If we can construct them better, then it would give us better LCCs. So at the moment we do not know. So there's a big question. Are there LCCs with r and delta both omega 1 and polylog n? So log n is the limit. So little omega of log n query complexity. We know that you cannot have it with log n, but slightly big. This is potentially true, and we do not, and open, and this is the best known query complexity, right?
So
yeah.
There are lower bounds which say less than logging query complexity is not possible.
That's correct. That's a result of Katz-Trevisan, who formalized the definition of locally decodable codes. And this is unlike the state with locally testable codes, where very recently such things existed with constant query complexity, and we're going to see this after. Okay, questions?
So what is the lower bound on the query complexity?
Log n.
Can
So
you say like a series of recent works that can prove that?
Oh yes. You're talking about where we don't insist that the rate is 1. Right? So this is the locally decodable code query lower bounds and locally correctable code lower bounds. Very recent results of Kothari and Manohar and a bunch of others, where they show, right. So there with query complexity 2 and 3 and 4 and such, we can study. We know that you cannot have positive rate, but we can talk about how does n vary as a function of k, and is it exponential or is it polynomial, and in some cases it is sub-exponential, surprisingly so, and in some cases there are exponential lower bounds. So the lower bounds are not surprising, but that they can be proved is surprising. Okay, other questions? Okay, so I have 30 I thought, so I haven't told you my favorite algorithm, and I may as well. Okay, good. So, and I haven't. So this is another topic. This is called list decoding of error correcting codes, and so I will draw some pictures, and I will state a very simple algorithmic algebra problem, which is about noisy interpolation of polynomials, generalizing the Berle-Camp-Welch algorithm, except it's for correcting even more errors. And I will describe a very nice algorithm for list decoding of read-solved numbers. Okay, great. So we are back in the setting of error correcting code. So we have codes. What is that? We have a subset C sitting inside sigma to the n. These were our points. And okay, and we know that if you start with a code word and you just go a tiny bit away, and you start at a particular point there, which is close enough to a code word, and then if you draw a ball of a certain radius, you only get one code word. But suppose you're in a situation where more errors have occurred for some reason, then one problem that you could consider is trying to get the list of all close by code words to an even larger radius. Okay, so this is so C is called eta L list decodable if the set of all code words X and C, so if for all received words, so for all received words in sigma to the n, if you draw a ball of radius eta around R, you do not get too many code words. Okay, so the ball of radius around R of radius eta n, if you look at that, intersect the code, this size is at most L. And if you have an eta L list decodable code, then it's reasonable to ask for the algorithmic question of find all code words. If it's eta L list decodable for L small, then you can ask find all code words in B of R eta n. So this is an algorithmic problem. Okay, and if eta was a delta over 2, then where delta is the minimum distance of the code, then we know that there's going to be at most one code word. Okay, so good. So there's a big question of what is the best list decodability for codes of rate R, and okay, so we're looking at codes of rate R, and we're asking what is the largest eta for which it is eta L list decodable for small l. So for given R, or maybe actually it should be given eta, because that's the number of errors I want to protect. It's given eta, what is the largest R? R such that there exist codes which are eta L, codes of rate R, which are eta L list decodable with L being, say, poly n. This is a good question. Now, or order 1, that's also a good question. And this is called the question of determining list decoding capacity. Okay, and this, unlike the question of rate versus distance for standard codes, which is really the question of eta 1 list decodability, this question we know the answer completely. So when sigma is 0, 1, R equals 1 minus entropy of eta. This is the best trade-off. And when
For each L?
for L equals order 1 or poly n. So this is achievable with L equals order 1, and more than that you cannot get with L equals poly n. So it's the strongest possible. So at this radius the list sizes are, I should say minus epsilon, at this radius the list sizes are constant. And when sigma is big, R equals 1 minus eta, minus epsilon is the best trade. So with the combinatorial problem we understand completely. Unlike the L equal to 1 case, where this problem we understand completely in the large alphabet setting, but in the 0, 1 alphabet setting we do not. Okay, so very recently there's been a lot of work on this problem. Very recently, I mean, say post 90s, which is so the problem of explicitly constructing such codes, I mean, we made a lot of progress, and this problem was recently solved. So this was solved by Guruswamy Rudra in 06, I think, maybe. And building of Parvaresh Vardi in 05, which, and this was a really spectacular use of algebra and, very, very, very clever and nice coding theory, and just math. Okay, so, but the seeds of that were about 10 years before with the list decoding algorithm for Reed-Solomon codes, which, so this is what I will talk about now. And in some way, there's still very nice open problems about this. So this is the list decoding algorithm, list decoding of Reed-Solomon codes. Okay, so we have our setting. We have sigma, which is in this case FQ. We have a subset S inside FQ with size S equals n, and and we have a degree parameter d, which is 1 minus delta times n, and we look at the code, which is polynomials p of alpha over all alpha in S, where p of x, degree of p of x is at most d. This was our code, and the list decoding problem is, so we are given a function r from S to FQ, and we want to find all polynomials p of x such that the distance between r and p, when you evaluate them on the set S, is at most eta. And then in this setting, the rate r is 1 minus delta. Okay, and we already saw an algorithm to solve this when eta is at most delta over 2. We know how to solve this. So this was the Berlekamp-Welch algorithm. So actually, this the problem of decoding Reed-Solomon codes up to half the minimum distance was already known to Patterson, maybe by Solomon and Patterson in 1960s. And Berlekamp-Welch is just another algorithm amongst the many algorithms which view this problem in many different ways, which does it. But this is the one that's going to inspire the next algorithm that we see. So in 95 or so, Madhusudan had a really nice algorithm. So this is Sudan's algorithm for list decoding Reed-Solomon codes. Okay, and it works for eta equal to 1 minus square root 1 minus delta, which is 1 minus square root r. So it's not quite 1 minus r, it is 1 minus square root r, so it's less than that by some constant. So it's, it's significantly away, but but the impressive setting for this is when r is tiny, then eta, which is 1 minus square root r, is 1, let's say r is little o 1, which is still a very reasonable Reed-Solomon code. You get eta, it's 1 minus little o 1. And what it's doing is it's finding a polynomial when even a negligible fraction of the values are correct. You're given claimed values for this polynomial, almost none of them are correct, yet you're finding the polynomial that's underlying it. You're finding a small list of polynomials, but it's really, it's a really pure and nice question. You want to find all polynomials that fit this. So, so I'm explicitly writing this out. This is p of x such that the set of all alpha where p of alpha equals r of alpha is at least 1 minus eta. Yeah, so, and this has a lot of implications. So this, along with the decoding algorithm for Reed-Muller code, the local decoding algorithm for Reed-Muller codes, gives you a local list decoding algorithm for Reed-Muller codes. This has a lot of implications in hardness amplification, in PCPs and such. Especially the fact that you can take radii as big as nearly 1. This has a lot of implications. And it's also just a very, very clean problem, and the solution is unbelievably amazing. Okay, so we will see this algorithm now. So we had this R. So the algorithm will be in 2 steps. The first step is to understand R. And the second step is to write down the answer. So 2 steps. Step 1, it's related to what happened in the Berlekamp-Welch algorithm. Understand R. How did we understand R in the Berlekamp-Welch algorithm? We found some equation that all the values of R satisfied. If you look carefully, what we found was a rational function that interpolated our polynomial. So if you look there we said we found E and N such that E of alpha times R of alpha equals N of alpha. This is the same as R of alpha equals N of alpha over E of alpha. So we interpolated a rational polynomial that fit our data, except when it's not defined where we were allowed to do whatever we want. We will now interpolate something else. We will interpolate a bivariate polynomial that explains our received word R. This is the idea. So we'll look for q of xy where the x degree of q is at most something and the y degree of q. So I'll say I'm making a choice, square root of n over k, and this is the degree of q, and degree in y of q is at most, this was square root of n k. And the y degree of this is at most square root of n over k. And my k is d. and if d is something like 0.1, and this is d is something like 0.1 n, then this is some theta n, and this is some constant. And it generalizes what happened here, because what we found, the kind of polynomial that we found here is, so I'm going to say what it is. This is like a degree 1 polynomial in y. So it's such that q of alpha r of alpha equals 0 for all alpha in S. Okay, so we have sitting inside fq cross fq. We have some points. This is alpha comma r of alpha for various alphas in the set, and we looked for a polynomial q of xy such that it's zeros. So the zero set of a polynomial q of xy looks like some kind of curve. That the zero set of q contains all the points alpha comma r of alpha. This is step 1. We have understood R. We try to find a polynomial like this with low degree in some controlled way, which vanishes at all these points. If we chose, this is the polynomial e of x times y minus n of x. If you took q of xy equal to this, then this polynomial vanishes at all the points, and this could be taken as such a q. Here we just allow larger degree in y. This is what's this is the way in which this is a generalization of the Berle-Campbell algorithm. Why can this be done? So before, if you remember, how did we know there was a solution to this?
More variables than the equation.
No, that's not how we did it then. We did it the other way. I gave you what e of x is. E of x is the error locator polynomial. We also realized along the way that there were more variables than equations, but we didn't use, that was not the source of our argument. But that is an observation if you make while doing the Berle-Campbell algorithm, you see that there was this other reason why this solution existed. That's the only reason we're going to use now. Now we cannot use the fact that there is a nearby polynomial to help us. Okay, so this is q. So why can we do it? How many coefficients does a polynomial with x degree this and y degree this have? Well, it's the product of the degrees basically, which is n. And it's actually this plus 1 times this plus 1 because I made it less than or equal to. So it's all okay. It's the number of free coefficients is one more than the number of constraints that I'm imposing. There are n equations. There are n plus 1 or more free coefficients. These are all homogeneous linear equations. Right? You know that whenever you have a system, actually it's a good quiz. Whenever you have a system of n plus 10 equations in n unknowns, n plus 10 linear equations in n unknowns, there's always a solution, correct? No, of course not. I mean, I said general linear equations. Yeah, okay, no, they have to be homogeneous, right? So first you think that, oh, it's true, and then you realize, oh, it's not. And then you think, oh, it's never true, but no, there is some situation where it's true and it's homogeneous, and that's the one situation we're using here, okay? Okay, so we found the q. Q of xy is some polynomial that has something to do with r. It captures r quite well. Okay, step 2 is to think about what, so we now just find the answer. So we have to think about what a polynomial p that is close to r, what relationship it has with q. Okay, so consider any p of x such that the distance between p and r is small. I haven't figured out what small is yet, so we'll see that in a second. Okay, then let's look at q of x comma p of x. What do we know about this? We know that it vanishes sometimes. Whenever r equals p, this vanishes. Right? So this vanishes. So I'm calling this h of x. This vanishes at any alpha which is an agreement point of P and R. So how many agreement points does that give me? It gives me, I guess, 1 minus small, which is so this implies that h of x has 1 minus eta roots. Also, the degree of h of x what's the degree of h of x?
The degree of p times
Right, p of x got plugged into the y variable. In the y variable, it's much lower degree. That's why we chose it to be imbalanced like this. That's degree d. This is root n over d. So when you plug it in, it becomes root of nd. This degree is root of nd, and you may have x and y monomials multiplied because I didn't say anything about total degrees or anything. So the total, so the degree of h of x ends up being at most 2 square root of nd. And this gives us, okay, so if this is 1 minus eta n, if 1 minus eta n happens to be more than 2 square root nd, we are in business. Then it tells us that actually h of x is the identically zero polynomial. And if h of x is the identically zero polynomial, it means something about p of x in relationship to q of xy. So if degree of h is less than 1 minus eta times n, then and this is the same as 2 square root nd is less than 1 minus eta times n, which is the same as reorganizing. So I have eta is less than n minus 2 square root of nd, which in this case is n times 1 minus 2 square root r. So I didn't get 1 minus square root r. There's some variant of this. It actually requires some deep idea, but there's a version of this algorithm. We'll give it with 1 minus square root r. It involves considering polynomials that vanish with multiplicity at these points. So taking this, if all this happens, then h of x is identically 0 as a polynomial. And this means that y minus p of x, the polynomial, divides q of xy. Right? So h of x, right? I mean, this is q of x, p of x is 0, and this is just the factor theorem rearranged, written in a different way, right? You know that if a polynomial vanishes at a point, then a polynomial y vanishes at a point, then y minus that point divides the polynomial. So this is some liberal interpretation of that. Okay, good. So this is the next step. So we did all this. This tells us that any polynomial that has high agreement with, the agreement, the distance has to be less than this. This is eta n. Any polynomial that has high agreement is such that y minus p of x divides q of xy. And so the algorithm part is factor q of xy. And when you factor, amongst all your factors, you will find various polynomials. Y minus p of x will be sitting as one of them. For any polynomial p which is close, y minus p of x will be sitting among them. Why can you factor? Okay, that's a whole different 6-hour lecture. But okay, it's done. I mean, at least it's a easily stated, clearly defined problem, which surely people must have been studying for centuries. Right? So they had been. Yeah. Okay, good. So this gives us the algorithm to decode from 1 minus 2 square root r. If you want to make it into 1 minus square root r, you have to do the most significant idea. This is due to Guruswamy and Sudan, which is to make the polynomial not just vanish at the point, but vanish at each of these points with high multiplicity. Yeah.
After factoring, we still need to go over all the polynomials, right? all possible polynomials, like, and check if the distance with the original one isn't.
Correct, right. And that is something you can do in linear time per
Yes,
polynomial.
We can go over all the polynomials because, like, instead of factoring, checking if two polynomials divide each other, it's easier. No?
So we did not prove an if and only if that the only factors of q of xy are y minus p of x.
Go over every polynomial.
Go over all the factors.
Check if it divides qxy.
Or go over all p of x's. Wait. So have we factored already or we're not factored?
No.
We're not factored. Oh, but there are so many p of x's.
Okay.
Right? The number of polynomials is q to the power n. Q to the power 1 minus delta times n. So this is like enumerating over all code words. So that we don't want to do. So factoring, you have to use some algebraic ideas to factor. Once you have factored, you get a whole bunch of p of x's. All the p of x's that showed up as y minus p of x's which divide q of xy. Not all of them may be close to r. There is no promise of that. Okay, so then you go through. Then you go through them and check amongst which ones of them are close to R. Check once you're down to a small list of candidate p of x's, then filtering that list down is okay. And the number of p of x's that you may arrive at this way is only square root of n over d, because every time a y minus p of x divides q of xy, it contributes 1 to the degree of q. Okay, so this can be improved to 1 minus square root r using vanishing with multiplicities. To improve the decoding radius even more, one has to consider different codes. We do not know today whether Reed-Solomon codes are list decodable to 1 minus r fraction errors. We know that random Reed-Solomon codes are list decodable to 1 minus r fraction errors. This is a very recent and flourishing line of work by, if it started with Gopi, Brackensek, Markham. And there's a lot of results in this area now. Random Reed-Solomon codes are list decodable up to 1 minus r fraction errors over linear size fields. They're not algorithmically list decodable, but it's combinatorially that the list size is small. Doing it algorithmically is a great open question. It's potentially true that all Reed-Solomon codes are list decodable over to 1 minus r fraction errors with polynomial list size. And if that was true, it would clean up a lot for sure. It's a really, really great open question.
What do you mean by random Reed-Solomon codes?
You choose the evaluation set at random. So, and it can be done with q being linear in n. So you take q to be some 1000 n and pick n random points within it and take that Reed-Solomon code. And so it's not algorithmic. That's a really nice open question. And it may be true that all Reed-Solomon codes are list decodable up to this way. We know that the list size cannot be constant. There are some examples over very special fields that sometimes combinatorially there are too many not too many, there are large polynomial number of polynomials near some received words. But there are variants of these codes, of Reed-Solomon codes, which are list decodable up to capacity. With this is the capacity here. One of them is called folded Reed-Solomon codes. That's the one introduced by Guruswami Rudra there. Another one is a univariate multiplicity code. So, so if after this you wonder, I don't even know a code that's list decodable up to capacity. The answer is no. You actually do know univariate multiplicity codes. What you don't know is why they're list decodable up to capacity. And that is a whole very long line of work again. So, okay, good. So, I guess that's all I have to say. Thanks. Questions?
So right now, for finding some explicit choice of evaluation points so that Reed-Solomon codes are list decodable, like what's the barrier? What do we not know here? So if the set is the whole field or whatever, then we know that you don't expect list decoding with constant.
Yeah, we know that we don't expect list decoding with constant field size, constant list size, but there are But then what's the barrier? Well, first of all, how are we going to prove it? Is it going to be an algorithm or is it going to be combinatorial? There's nothing to work with. At least with random, there's something that's moving. Otherwise, it's just sitting there. I guess it has to be some kind of algebraic proof. It's not generically true that every code of distance delta is list decodable up to radius almost delta. It has to be some kind of algebraic proof involving the structure of polynomials in some way. I have no idea how such a proof would look. I think more likely than not, it is not list decodable up to list decoding capacity. But I really hope it is. Other questions? Okay, great, thanks.